Okay. So for energy work and power, right, there are a few things that you will need to know. First of all, you need to know that there are different types of energies available. For example, there is kinetic energy, there is potential energy, of course, there's also light energy and sound energy. But in our focus for this chapter is mainly the two main one is kinetic energy and potential energy. And within potential energy, there's also subdivision of types of energy. They have your gravitational energy. Okay, that's the one that is actually the one that is exerted by a gravitational force. Then you have your elastic potential energy. Those are like your rubber band, where there's some form of stored energy. And then of course there's the chemical one, so things like from your battery and whatnot. So potential meant storage, energies that stores. Whereas for kinetic energy, kinetic comes from the word movement. And when we talk about kinetic energy, we are talking about how things are moving. So there is a very one of the main assumptions is that whenever there's a storage of energy, there is also a transfer into moving energy. And this is usually what we see in most examples in O level. But that doesn't mean it happens in real life because there are other kinds of energy that is also produced from or converted from potential energy. You have like a sound and heat, like when you're walking. Walking is a moving action. But at the same time, you might generate some form of sound when you walk. And that is so in terms of the energy, it is not just creating the kinetic energy, but it also releases sound. It transforms into sound energy. Um, One very important thing is principle is that energy, right, cannot be created or destroyed, meaning that it can only be transformed or changed from one form to another form. You can't produce energy, you can't destroy energy. Okay, so energy is this ability to actually do work, and how do we measure energy? Is used the SI unit joules, and they come like what we say. They come in many different forms. The principle of conservation of energy. This is one key thing that you have to remember is that energy cannot be destroyed and it cannot be created. It can only be converted from one form to another form. So let's say storage to sound, storage to light, potential. Sorry, we try not to use the word storage. Potential energy to light energy, potential energy to sound energy, etc. And that the total energy during the transformation is constant, meaning in that environment, if you have like maybe 10 joules of energy, the end goal will still only have 10 joules of energy. Okay, in a closed environment. So how do we then calculate kinetic energy? And kinetic energy is this ability to do work through motion. So the formula for kinetic energy is actually half mv squared, where what we say by half mv squared means half times m, which represents the mass, times velocity squared, where you in other words, you can actually rewrite it as half times mass times velocity again, so v squared. Now, the SI units for the respective one is also important where you need to know mass is in kg, speed, velocity, in this case, is actually in meter per second. You may need to do the conversion. If let's say you km per hour, we have to convert it to meter per second. So these are things. But generally, we use meter per second because we tend to see motions quite small. Sometimes bigger one, we don't see a long term kind of movement. It's only short distance travel. So in this case, when we look at the kinetic energy, when a 0.5 kg trolley moves across the floor at a speed of 1.5 meter per second, you would see that the mass is 0.5. For speed, a lot of students tend to make the mistake of calculating it as acceleration. And when you use acceleration, it's in meter per second square, and that's wrong already. So do have a distinct difference between velocity and acceleration. And then what you do is just put in the formula, you get your answer. You try to also write your answers in standard form that will allow you to write things in 3SF and things like this. Okay. The SI unit for energy is in joules. Next, we look into the other one, which is potential energy. So potential energy is actually energy stored in objects when they are lifted above the Earth's surface. So when an object of mass m is raised to a height h, there is some form of gravitational force acting on it. That's why we call it weight. However, if you look at, like, let's say a box, putting on a table, yes, there is a mass, but the weight, there's also weight lah, because even though because if there's no weight, what will happen? The whole box will actually float around. So that's what we meant lah. Right? So what happened is there must be some form of possession of gravitational potential energy for you to calculate this, and that the formula for gravitational potential energy is actually mgh, which is mass times gravity of Earth times height. So, because gravity on Earth is different from gravity in the moon and etc. So, the gravity here we speak about is the gravity on Earth, and that's where it's around 10. Okay. So when we talk about height, right, especially this particular scenario, um, some common mistake is that students will use the distance of the the line of action. Oh, this is wrong. So when we talk about height, we are talking about vertical height. There's some form of 90 degrees angle to it to the base ground. And that is what we use actually. So in exam questions, they will tend to confuse you with a lot of like this kind of information. But the gist is you have to be very comfortable in selecting the correct values for that particular area. Okay. And so the conversion of energy involving kinetic energy and potential energy, because of the law of conservation of energy, we recognize that energy cannot be created or destroyed. And even so that energy can only be converted from one form to another. So the total energy is conserved or unchanged. So the sum of the total kinetic energy and the potential energy is what we call the total mechanical energy. And then these total mechanical energy must always be the same before and after the event. That means if let's say I supply 10 joules of kinetic and potential energy into a system, into a machine or what, only 10 joules of energy will be produced from the system. Okay. So for example, it's like a pendulum lah. When you release the pendulum from a certain height, it will just keep moving in oscillation. Now the thing about this is, some of you may ask why lah. I mean, if we are not introducing the energy, I mean, we are releasing the pendulum, right, and it moves, right? Why does it stop? If the law says that the total amount of energy is the same, right, that means the whole pendulum should still continue to move because the energy supply is always there. So that's the thing, you see, on where in the environment, right, what we have other kinds of forces at work. For example, we have air resistance, and friction. Sometimes that slight motion of the pendulum release may also have the string, the rope, right, actually causing friction with where the anchoring point is, leading to conversion of the energy towards heat. So there's heat loss, heat energy loss. There is also maybe sound energy that you very very minimal that you lose over time. So these are things that cause it to slowly lose the total energy to the point that there is no more total energy within the system. That's why the pendulum stops. So that's usually what happens. But when it comes to theoretical understanding, because we don't want to overcomplicate things, we always assume that the heat energy and the sound energy is negligible, the loss is negligible. Hence, whatever calculations we tend to do is that for the total mechanical energy, Ke plus Pe is always constant, meaning the pendulum will always keep moving because of the same constant supply of energy. That will also mean that the total mechanical energy is always conserved at any points of the motion of the slope. Meaning, right, the total kinetic energy, the total mechanical energy here is the same as here, the same as here. Because number one, potential energy is usually influenced by height. So at different heights, right, one would actually assume that potential energy is different, it's changed. Correct or not? But then, in this case, right, when you have a higher potential energy, you have a lower kinetic energy. because they have converted, and hence the overall total mechanical energy is always the same. Next, a ball of mass 40 grams is fired from a source horizontally at this speed, then it collides, and therefore, I mean, like, this is quite straightforward, lah. How to find kinetic energy? Usually half mv squared. How do you find potential energy? Is mgh. But the key thing is this statement here. So why is PE equals to potential? Sorry, not this. I think it's a wrong question. Yeah, I think that's just a formula for potential energy. But later on, right, we'll be seeing that for potential energy, due to the total internal energy conservation thing, we would realize that kinetic energy in some way will be equals to your mgh in some form of relation. Okay, later on we will actually be seeing some of the situation that this can occur, but what is the main thing is we have to recognize this portion here, that regardless of the points, right, the total mechanical energy should always be constant. Next, we look into work done. So work done is usually defined as the product of a work and the distance moved in the direction of the force, in which the SI unit for work done is in joules. So the formula for calculating work done is W equals to FD lah. Okay, where force is where work done equals to force times distance. Now this distance is very big. So what is this distance? This distance has to be in the same direction of where the force is being applied. So let's say you're pushing a box forward. Okay, so let's say I draw the ground, the box is here, and you're pushing the box in this motion. The distance of the box is actually this, because it is in the same direction and in line with the slope of the area. But then, if let's say you walk up a stair, where is that distance then? Is it the diagonal distance? Is it the distance moving up like this, or is it this distance? So that is where we have to be very mindful with a few things. Number one, where is the force exerting? So like let's say we are carrying an object upwards. Like we bend down and then we carry the box up and then we move up the stair. You realize that the force acting against you is actually gravity, and hence what you are doing, you're exerting your leg strength to push the box up. So the distance traveled by the box that's in line with the vertical force motion upwards, right, is actually the height of the staircase, or the height of yourself lah. Okay, so work done in lifting up a box in the absence of friction is quite straightforward. It's just a vertical height. Work done can also be done in pushing a box up the slope. So in the sense that if let's say you're not talking about a staircase, you're talking about a slope, right? And you're pushing, you see the same direction of which the force is moving in a diagonal action. The distance would then be the wooden plank, the distance of the wooden plank rather than the height. Why? Because the force exerted is pushing along the slope. It is different from carrying a box upwards, vertically upwards. So that's where we have to make that constant differentiation. And the SI unit for work done is in joules. So one interesting thing from here is that we could see that because energy and work done shares the same SI unit, they tend to be interchangeably used, but they have different meaning because kinetic energy has a different formula from potential energy, which has also a different formula from work done. Okay. Next, we look into power. So power is usually defined as the rate at which work is done, or the rate at which how the energy change. That means how much potential energy is converted to kinetic energy, etc. And that is why for the formula of work done, because it's a rate, it is basically work done divided by time. okay, in which it's actually the same as energy divided by time. Now, what is the SI unit for power is actually in watts. Work done is in joules, and of course, time is in seconds. But power can also be used in the form of kilowatt. Let's say you're using a lot of power, like let's say electricity from power station. So all this you can actually use interchangeably. Just be mindful of when you use watts, your work done SI unit is in joules. You have to convert from kilojoules to joules, and then your time you have to reconvert it to seconds. Okay. Another, some books may actually use, they will not write watts, actually they will use joules, they write joules per second as their SI unit. This is not wrong, this is also correct. Or some may actually use kilojoules per minute, etc. So generally, whichever format, as long as you use the correct units, I think it's fine. So that's generally it for power. Okay, let me try to find, yeah. So let's say we look into this particular example too, as a narration before we end this particular item. A car has a mass of 2000 kg. It accelerates from rest to 3 meters per second in 12 seconds. So there's some form of, like a slope kind of acceleration already. Yeah. And then the frictional force is 300 Newton. Calculate the force exerted by the car engine. So in this case, when you want to find force, you must remember the formula. You recap the formula, right? It's actually F equals ma. So this chapter, right, is very related to the chapter on force. Not so much on moment, but more on force. Okay, and in this case, what we can see is that acceleration is your 3 minus 0. So your final velocity minus initial velocity divided by 12. Your acceleration will be 0.25. Then using the formula to find the force, and you know the mass of the car is 2000. Okay, assuming that that's the car engine. So 2000 times 0.25, you will actually get 500 Newton of force exerted by the car. But one other thing to take note is you have to consider what is the amount of force applied by the engine. This is the overall net force due to the motion. But there's also frictional force that is going against the motion. And they want to find the engine. So let's say engine is moving forward, friction is an opposing force, so it's moving backward. Overall resultant force is moving forward. What you have for 500 Newton is actually the resultant force of moving forward. But the question asks for force applied by the engine. So that's where a lot of students would then make the mistake of 500 minus 300. Why? Because they thought that 500 is not the resultant force, but the force applied by the engine. And then you get a wrong answer. Rather, this resultant force is 500. When you redirect the equation from a negative force, frictional force, to add the resultant force, you would then get the force applied by the engine. Next, what is the total work done by the engine during the acceleration of the car? So that's where you will need to look into work done. What are the ingredients that are required for work done? You need to find force, you need to find distance. And for a velocity time graph, if you remember the chapter of kinematics, it's towards drawing the graph and calculating the area under the curve or area under the line. So in this case, you draw it out, find the distance through the area, you get 18. Now, a lot of students don't draw this, so they will get stuck in this question. By drawing, you know the distance. Once you know the distance, you can find the force. I mean, you can find the work done, and F times T, and you'll get the answer. And power is quite straightforward. You already have everything. You have the time, you have the work done, and therefore you got the answer. Now, another common question that they tend to ask students, right, is in relation to work done, right, is there any work done in this particular situation? So it can be a situation where there's a wall and the person is pushing against the wall. Okay, they're pushing it. Is there work done? Now you must look at the formula again. W equals F times D. Even if I apply force, I'm using all my strength, in my hand and pushing against the wall. The distance is actually zero. I do not see the wall moving. And if the wall is not moving, then whatever force you applied multiplied by zero, your work done will also be zero. So you are not generating any work. It's just like you are given a homework to, if let's say we are given a homework to do, and then we just use our brain power and think. But then but we are not writing down our answer. Is there work done? There's no work done. Even though you are thinking, okay? I mean, it's one such analogy lah. And then of course, when we look into power, power is red, right? So let's say, um, if you can think of it as power in the form of how fast you complete your work. So the higher the power, that means the faster you are able in completing the work done. So in a way, if the wall is always stationed, it's like not moving, even though you exert a lot of force, there is no work done, and therefore you have no power. So that's how formulas in physics they tend to link with each other. And that is the main idea of energy, work done, and power. Okay. For energy and work, for the part of energy, questions that are more related to these are either a bouncing ball kind of question, or a ball actually sloping downwards from a height. So these are some questions they can ask. Parachute kind of question, when someone jumps from a parachute, how are the force is moving and things like that. Work done would be more towards of like walking from one end to another end. A trolley question, there must be some pushing and pulling action. Okay. And then of course, power is just another layer upset, where they want to understand how much power uh, to invest in the engine. They may even give you some conversion of cost related to the power of engine, and which is more, and ask you to make a recommendation as to which is actually a more cost effective engine to buy for a car to deliver the amount of work done and everything. Okay. So that is all for this particular chapter. Then I'll look forward to the next one.